सादर नमस्कार, सुस्वागतम, अभिनंदन, केम छो, वणकम, आदाबा, सत श्री अकाल, खंबागाड़ी, वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का पीआरएल के अमृत व्याख्यान के 106वें अध्याय में स्वागत करता हूं, अभिनंदन करता हूं। आई अनिल भारद्वाज वेरी वार्मली वेलकम यू ऑल टू द 106th पीआरएल का अमृत व्याख्यान। We know that we started the PRL Amrit Vyakhyaan as a part of celebration of PRL's 75 years of establishment, which coincided with Azadi Ka Amrit Mahotsav, that is the 75 years of independence of India. And that was meant to celebrate the rich legacy and history of the contribution of PRL to physics and space sciences, and as a tribute to Dr. Vikram Sarabhai. And it all started on 4th of August 2021 with a sankalp that every Wednesday 4 p.m. we will have PRL Amrit Vyakhyaan. We completed the 75 PRL ka Amrit Vyakhyaan uninterrupted in January 2023, and subsequent to that we took another sankalp that every month we will have one PRL Amrit Vyakhyaan. So today is the 106th PRL Amrit Vyakhyaan, as well as a part of the monthly Vyakhyaan. And for this Vyakhyaan, we have yet another very distinguished Vyakhyaan Karta with us, Professor Dipankar Banerjee, who is the Vice Chancellor of Indian Institute of Space Science and Technology, that is IIST in Thiruvananthapuram, which is the academic wing of Department of Space Science. And he is going to talk to us on a very pertinent topic or very contemporary topic, that is recent heliophysics missions launched within the last 2 years and the role of Aditya L1. As we know that Aditya L1 is the first mission from India to study the sun, and it is at L1 point. We will hear from Professor Dipankar Banerjee about what other missions are happening or have happened in the past and how Aditya L1 is playing a big role in study of the sun. We thank Professor Banerjee to agree to our invitation, in fact, a very short notice invitation, and to be with us today to give this Vyakhyaan. And I will now request my colleague, Professor Pallam Raju, to formally introduce our today's Vyakhyaan Karta to our audience at the WebEx panel, as well as those who have joined us live on the PRL's YouTube channel. So over to you, Professor Pallam Raju.
Thank you, Professor Bharadwaj. It is indeed a pleasant duty for me to introduce today's speaker, Professor Dipankar Banerjee, who has, as was already told, he's the Vice Chancellor of the Indian Institute of Space Science and Technology in Thiruvananthapuram. He did his bachelor's degree in physics from St. Xavier's College and master's degree in theoretical physics from the University of Kolkata. He obtained his PhD from the Indian Institute of Astrophysics and completed a couple of postdoctoral tenures before he returned back as a faculty at the Indian Institute of Astrophysics. Later, he served as the director of the Aryabhatta Research Institute of Observational Sciences, also called ARIES, in Nainital from 2019 to 2024. Before joining as Vice Chancellor at IIST in 2025. Professor Banerjee's area of research is sun and solar atmosphere. His work involves theoretical and numerical modeling using data from ground and space-based instruments. His work has enriched our understanding of the sun and its impact on the space weather. He is the co-chair of the science working group of the Aditya mission. He is also involved with NASA's Punch mission. He is a fellow of the Indian Academy of Sciences, National Academy of Sciences, Royal Astronomical Society, and is currently the president of the Astronomical Society of India. Professor Banerjee has more than 150 peer-reviewed publications with more than 3,900 citations. Apart from his quite engrossed scientific career, Professor Banerjee has developed interest in many other activities. He's a trained Hindustani vocalist and is also part of the Bengali theatre group Smaranik, and regularly performs in plays, participating in national and international theater festivals. And as I understand, there's another one coming up next month, so he's really going towards that, preparing for that. Professor Banerjee's love for science and zest for life are infectious. However, today he's going to talk on his very pet topic of the sun and solar atmosphere, and he's going to deliver the 106th PRL Amrut Vyakhyaan on recent heliophysics missions launched within the last 2 years and the role of Aditya L1. With this brief introduction, I'll invite Professor Banerjee to begin his Vyakhyaan. Professor Banerjee, over to you.
Thank you very much, Pallam, for your very kind invitation and also the very kind introduction. So I hope I can live up to the standard of the series what you have here. Let me just confirm that I'm getting into full screen mode. Are you able to see the full screen?
Yes. Yes.
Okay. Thank you again, and it's a privilege for me to be, able to give a lecture in this very, pronounced series. I think I have given a lecture a few years back in the same series, so it's really nice to be back again. So what I intend to do today is to take you through this particular slide, which gives you an overview about the heliosphere. So here you see our nearest star, the sun. So there are internal properties of this star, sun, which dictates the changes in the surface and in the atmosphere, and that effectively also affects our heliosphere. And finally, the interaction with the planets. And now we all know that the space is very important for our living, just not for our atmosphere or our climate, but much beyond our daily life, which is also known as space weather. So I will not probably go to too much of detail on the space weather, but this particular slide gives you an overview how the activities in the sun and its variation is affecting the entire heliospheric atmosphere as well. I know at PRL you have a really multidisciplinary expertise all the way from physics, plasma physics, astrophysics, atomic physics, and beyond. So I would have loved to take you to different parts of the sun and heliosphere to really highlight how different physics is very much linked with the study of the sun. So here again, I'm showing the same plot, but trying to describe it in the physical conditions, how it really varies, all the way from interior of the sun, where the thermonuclear reactions are happening. The density scales of the density, varies of 7 orders of magnitude all the way from interior to the sun to the outer atmosphere. So you can imagine that that the physical conditions, if it varies, the physics what we apply at different parts of the solar interior or the surface of the atmosphere and beyond are going to be slightly different. Here, I'm just going to highlight one particular parameter, which is called the plasma beta. Primarily, it governs the ratio between the plasma pressure and the magnetic pressure, which subsequently dictates that where it is the fluid motions will dominate the dynamics, and which are the regions where the magnetic field will dominate the dynamics. So here we know that in the interior of the sun and all the way up to the surface, the plasma beta values is much larger than the one. So it's the fluid motions which dominate. So the normal hydrodynamical descriptions are reasonably sufficient. Whereas if we go into the atmosphere of the sun, and namely the corona, which is the outer atmosphere of the sun, we all know, there the plasma beta value is much less than 1. And there it is the dynamics of the magnetic field or the changes of the magnetic field dictates the motion of particles as well. So whatever dynamics, whether it is a big ejecta or whether it is instability, all these are primarily driven by the changes in the magnetic field. And so these events like flares and CMEs or the plasma winds, which we call it solar wind, they're all governed by the structure of the magnetic field or presence or absence of the magnetic field. So magnetic field becomes the most crucial parameter for controlling the dynamics in the atmosphere. And then when we go closer to the, again, the planetary atmosphere neighborhood, in those regions, again, since we are much, much away, the density values are also much larger, interparticle distances are also much larger. In those scenarios, again, we have a situation where the plasma beta is much larger than 1, and probably the hydrodynamic or the kinetic descriptions are good enough. So that's the different domain over which we solar physicists somewhat work. And again, I will highlight that the niche areas in the solar physics, what we want to really focus on, one is this solar interior, the study of the interior properties of the sun by looking at the surface oscillations, which we call a helioseismology, the dynamo theory, which dictates the evolution of the magnetic field on the surface and beyond. Then when we come to the surface, these magnetic fluxes are emerging in the surface, the sunspots are born, but then the sunspots are there at some time, some spots are not there at other occasions. So there is a evolution of the large scale magnetic field over a long time scale, which we call a solar time scale. But then there is also, a time scale where we study the magnetic flux emergence in much shorter time scale, seconds to minutes to hours. And that is what is really giving you the space weather effects. So following the photospheric features, whether it is sunspots, whether you go slightly higher up, there are other, atmospheric features like filaments, prominences, pludges. You follow their behavior to study these, dynamics. We go slightly up in the atmosphere, and we know this is again a mystery of the solar atmosphere, that the outer atmosphere of the sun is much hotter than the surface. Initially, we were in a puzzle that how is it possible thermodynamically it cannot be explained that in an atmosphere where you are away from the source region of the heat, you have higher temperature. So now we know there are lots of non-thermal processes which are responsible for explaining the higher temperature of the outer atmosphere, namely the corona. And then there are also challenges in terms of diagnosing these different layers of the atmosphere of the sun by spectroscopic method, by spectropolarimetric method. One of the biggest challenge in the magnetic field, understanding or observation is that we do not have a very good way to measure directly the magnetic field in the corona, because the spectral lines are very weak, and the magnetic field effects, namely the Zeeman effect and all that, is almost very tiny to measure it. So there are alternative way of studying the properties of the waves which we see in the corona. You can get some inferences about the magnetic field. So that's a field of called coronal seismology. And then, as I indicated, that there are a lot of these dynamical structures which you see are transient in nature in the form of flows. There are jets, there are spicules, there are these different flares, and the bigger structures, the coronal mass ejections or the CMEs. So all these different objects need to be studied by different kind of physical models, different kind of physical diagnostics, and that demands lots of new observations. And that is what I will take you to, that the recent development in this observation. And then the other major global thing is the angular momentum transport in form of the solar wind, and how it is connecting the sun and the near atmosphere and the beyond. So that's again a very important subject area. But again, since solar global magnetic field also varies with a longer time scales of 11 years, we call it solar cycle. We now know that this global picture of the solar wind is also varying with the solar cycle time scale, and that makes a control of the CME propagation through these solar wind, which is very different at different epoch. So heliosphere and the space weather is the new frontier where a lot of focus is, which is dealing with the CME evolution in this interplanetary space. Now we need to really find out, once a CME is ejected from the sun, what time it is going to arrive at different vantage point in space. It could be at Lagrange one point location, it could be near Earth, or it could be another location, because we have now missions which is at different vantage points, and that is really improving our understanding of the CME propagation. And then eventually, once we can characterize the properties of the CMEs, their energetics, their kinematic properties, their magnetic field properties, then we will be able to study their impact as it comes into to the planetary magnetosphere. So these are really different domains where solar physics demands observations, because theory can be only matched or improved with the help of inputs from observations. And thankfully, we have several observations. And then, of course, the knowledge what you get through the solar physics research, you actually apply to other stars. You look for stellar flares, you look for stellar CMEs, stellar quasi-periodic pulsations, which is again related with the seismology, what I was talking about. Then also the big question about the planet habitability, like if the planet has a magnetic field or not. If it has a very weak magnetic field, then how that planetary atmosphere can sustain with this existence of the stellar wind. So that way, the star-planet interaction and the planet's habitability, even this extends actually beyond exoplanet discovery and their existence as well. So this has I would say that the solar physics do have now a larger impact on the stellar and
Is there an issue at the Dipankar side?
Yep.
I
Yes,
think
it looks
he
like.
tried. I'm calling him.
Yeah, is there any problem?
Your
Yeah,
video
I
has
think.
gone.
Hello?
Yeah.
Can you reshare
Sir.
your video?
Okay.
Yeah, I think you were turned off sometime.
Oh, I see. Are you able to see my screen now?
Yes.
Yes.
Oh, there was a drop in some data. Okay. Yeah,
Yes.
thanks for. So how much time I was dropped
No,
out?
just now only. I think you were just talking about this
Maybe a
slide.
minute or so.
Okay.
Yeah.
Okay. Fine. So again, coming back to our nearest star, this solar atmosphere, which is revealed from Solar Dynamic Observatories, one of the UV channels, 171, which is probing the plasma of about 0.8 million K, provides us a new view of the plasma diagnostics as well. So as I was mentioning that I know PRL has a really multidisciplinary areas. So I would have loved to give you even more insight about how plasma physics is applied in different solar physics, whether you call it atomic physics, particle physics, nuclear physics, spectroscopy. I can actually connect you with some observations from the sun. But I will not do it today because of limitation of the time. So I will move on. This is an environment where the CMEs are propagating near the sun. So this is a image again, or a movie from Parker Solar Probe. This is, of course, our probably most sophisticated space missions, what we have for the study of the heliophysics from NASA, which is looking very close to the sun. It is so close that we can't really look directly to the sun. We are looking away from the sun and trying to see or track these ejecta as it comes. And as you can imagine here, this ejecta, when it comes, it's not a really very pleasant environment. So I will be talking a little bit more on this particular object, namely the CMEs today. And the other aspect which I referred to today is about the stellar wind or the solar wind here. What is plotted here, the lower panel shows the sunspot number with time. This is the 11-year solar cycle which I was referring to. So there are periods over which there are hardly few sunspots. We call it solar minima. And there are periods over which there are lots of sunspots available. Sun is magnetically very active. We call it solar maxima. Now, this is a picture of the solar wind, which is recorded by Ulysses in its first orbit. So here, the solar wind velocity in the polar regions is about 700 kilometers, whereas the equatorial region, it is only about 200 to 300 kilometers. So it looks very clearly that during the solar minima period, we have a very asymmetric solar wind, a fast wind which comes from the polar region, and a slow wind which is coming from the equatorial region. Now, if I go to the phase of the activity maxima or solar maxima, that time the solar wind is very, very mixed. And it is not so preferential that, in the only very wide polar regions, you have the fast solar wind. The fast solar and the slow solar wind is very much intermixed during the solar maxima. And then again, when we approaching the next minima, Ulysses has revealed that the same behavior is repeated as we saw in the first orbit. So it is very clear that the solar wind is the background, right? Now, if I actually inject a CME on the solar wind, there is an interaction of the CME with the solar wind. That will dictate when the CME will be arriving, at Earth or any other vantage point in space. This is very similar to, you can think about a situation we used to play in our childhood, throwing a stone on the flowing river, and we used to see how the stone is going to follow the river, how fast the stone can go in the river. So here, very crucially, you could see that the CME propagation is heavily modulated by the nature of the solar wind. So a comprehensive understanding of the solar wind and the CME and the background, coronal or heliospheric conditions are all equally important. So now that is making it very much demanding that the CME propagation just cannot be, estimated based on when it is coming from the sun, where it is coming from the sun, because of course the CMEs comes with a very different speed initially. Some may come with few hundred kilometers, some may come with 1,000 kilometers, but just 1,000 kilometers is not going to maintain that 1,000 kilometers all the way. It is going to interact with the solar wind. So you have to account for all these interaction of the drags and so on. So that's a domain which we are working. And as I have now getting into the field of, where do we stand in the global scenario of heliophysics system observatory. So here again, this image gives you an overview of the number of operating satellites in heliophysics alone. So there are 20 operating missions with 27 spacecraft. There are 13 missions in the formulation or the implementation phase, 1 under study. This slide is slightly older because now we have, again, which I will be talking about today, the Punch is already launched, Prova 3 is already launched. And in all that, we have started little late, I will put it that way, but we are actually not doing so bad because we have reached a location in the heliosphere which is very, very important in terms of the studying the sun, namely the Lagrange 1 position. As you can see here, there are other Lagrange 1 satellites, namely the SOHO is there, ACE is there, WIND is there, but with a new set of instruments at Lagrange 1, looking at the continuously at the sun, because once you have at Lagrange 1, you have the advantage of looking at the sun continuously. And the other very important thing is anything coming towards Earth, before it reaches Earth, it has to pass through the Lagrange 1 location. So that way you have a possibility of remotely looking at the sun with the remote sensing instruments, and being at Lagrange, you have a possibility of having a set of in situ instruments. And then a combination of these remote sensing and in situ instruments allows you to do a much better comprehensive understanding of different solar phenomena as we study. So that way, I would say that, we can't work in isolation. This is also very important. And in my talk, I will try to emphasize that again and again, how important it is particularly for the younger generation to really have a sort of view of a comprehensive view of the solar physics phenomena And for that, you need to really look at other, satellite data. Many of them are in the, in the open data domain. And of course, Aditya also, we have now open data. And with that, we're in a much better, situation. So what I plan now next is to very quickly go through the very recent, few missions which are contemporary and very much complementary in nature with Aditya. Namely, this PROVA 3 is a technology demonstration mission. It is very similar to our SpaceX experiment. Two satellites, they were clubbed together. They were into space by PSLV, our own launcher, in first week of December last year. Once they are into space, they got separated, and they are trying to create a total solar eclipse kind of conditions in space by formation flying. This is one of the crucial technology demonstration what they are doing for a very highly elliptical orbit. Our SpaceX experiment is more of a circular orbit, but here they're in a very highly elliptical orbit, and when they're much away from the Earth, they are creating this formation flight. So what you can see here is one satellite is creating the shadow of the solar disk, and the second satellite is sitting in that umbral region of the shadow. This is precisely what we try to go in during the total solar eclipse conditions. During the total solar eclipse, you have to be in the totality path, and here precisely this second satellite is going to be in this umbra. And what they have achieved already, they are maintaining a separation of 150 meters, very, very precise, with a precision of 3 meters. And the shadow which is falling on this particular location, you can see the shadow here. This is the first satellite is working as an occulter, and here you have the shadow. And the precision with which you have to maintain the shadow is 10 millimeter. That means the lateral movement of the satellite is allowed up to 10 millimeter precision. So this actual formation flying accuracy has been achieved, and thanks to a suite of onboard positioning technologies and this autonomy in space. There is no ground command which is actually doing this. It is completely autonomously achieved in space. So this is, I think, a huge technology demonstration. This is the first flight images. Again, credit to the ESA team. They have shared the first flight images. I was there in a couple of weeks back to interact with the Science Working Core team. We do have other, very, very interesting things to be seen also, but we are not making it to the public domain yet. You call it jets, you call it prominence eruption, you call a CME eruption. Everything is now being seen from the PROVA 3. But you can see how beautifully the eclipse like images are now obtained. I must admit that from our own coronagraph VLC, we were hoping that we will be also getting this kind of view, because the field of view of this PROVA 3's aspect coronagraph is exactly the same, but we still have a problem with the scattered light with our continuum channel, so we have not been able to achieve that. But we have got some spectral images, and I will later on compare with some of these. So this is visible total brightness. They also have a polarization measurement, a polarization brightness. You see the prominence, how how spectacularly they're able to capture. So this is through helium spectral line, and then this is the green line. This is exactly the same filter image along with our VLC. So how important it is to have joint observation, I will again reiterate that. And then again, they are combining these PROVA 3 images to just superpose with any on-disk images, and then a coronagraph, which is looking at a larger distance. You can follow these structures. So the final structures, very, very close to the corona with white light, what we have seen in total solar eclipses images with lots of processing is now revealed from space. And so we can create an artificial eclipse for 6 hours, almost anytime we want, with this, formation flying. And that is what is going to happen for the next 2 years. So that's a very quick run through with the PROVA. I will quickly run through the, payloads on Aditya to put things on context. We were launched in early September. Then we got into L1 insertion in early January. Then there was a guaranteed phase for validation and and getting the data pipeline ready and so on. We already completed one full halo orbit, and then 2025 onwards, early, the data has been made into the public domain. January, it was released, and now as and when data is coming, it is actually available from ISSTC as well. And then there are announcement of opportunity for joint observation. I am aware there are quite a few joint observations are already happening with Solar Orbiter. I'm not going to talk too much on the Solar Orbiter because that's why I chose this 2-year window, so that I can focus a little bit on the Proba and the Punch thing along with the Aditya. So again, coming back to the Aditya's observatory class, we have multi-wavelength capability from X-ray to near UV to optical, and then the particle detector. So we have a combination of 4 remote sensing and 3 in situ observation, establishing connection between the source and the in situ. That is what I was referring to. When we are at Lagrange, we are looking remotely to the solar disk and looking at the different features on the solar atmosphere, looking at integrated flux from X-ray flux coming from the sun as a star, and then an in situ measurements I will talk about very briefly. I will also must point out, I know PRL has this expertise in the particle detectors, and the major instrument in the particle detection, namely aspects, is made at PRL. So you must be hearing a lot more from PRL on those results. So today I'm avoiding that. I'm not an also subject expert on that. So I'm going to little bit focus more on the remote sensing for sake of comparison with the other 2 missions as well. So in general, it must be also pointed out that it is an observatory class mission, and it has a possibility of addressing many scientific problems. So it is up to the scientists how they can exploit the different modes of observation from these, particularly the remote sensing instruments. Again, as I iterated, that we are at Lagrange 1. So we are looking at the solar ultraviolet imaging telescope to the full disk image of the sun. We're looking at the coronagraph to look at the 1.05 to 3 solar radii distances. We have 2 X-ray spectrometers, which is looking at sun as a star and looking at X-ray fluxes and the spectrum in X-ray in high energy and the low energy bands. We have these 2 particle detectors, namely the PAPA, and as I indicated, the major, I would say, the bulk, particle detector instrument called Aspects, built at PRL Ahmedabad, and the lot of members, I hope they are on board today there as well. And we do have a magnetometer as well. Very quickly glancing through that, there are now quite a few observations of the SOOT instrument. This is looking at near UV, primarily the chromospheric heights of the solar atmosphere. We have several filters, and this is also one uniqueness, that these particular magnesium filter regular observations have not been there from space platform much. So we are looking here again on the solar active regions. You see these locations where normally the flares take place and the most of the dynamics originate from. So by combining our chromospheric observations with some of the solar orbiter, is going to be a very, very crucial element. Here I will give you again very quick examples of observed X-class flares and CMEs. Couple of examples. So again, as I mentioned, we are looking at the source region of these huge ejecta. Earlier, I have shown you, movies of these huge ejecta when it is traveling away from the sun. So here, these 2 examples are showing you when they are really, really in the early phase of evolution. So that's again a good capability, and we can really see what is happening in the source region, what is the time scale of these evolutions, and so on. So we do have good observations. This is a couple of papers which is already published in Abjad later. Then we have this first multi-payload science from Aditya. Again, primarily the remote sensing instruments here. From the SOOT instruments, we are looking at the source region, how these 2 active regions, they interact with each other, at what time scale, and then what kind of responses you see in the overall fluxes. We compare with the AIA. This is a Solar Dynamic Observatory EUV imaging instrument. Then we have GOES X-ray fluxes. And then again, as you know, with the comparison with again the international facilities and capabilities of your own payloads. Here, this is the example of how the different filter fluxes from this region, where this source is, how it relates with the integrated flux, what we see eventually when it's coming out of the sun, how they are correlated in time and space is the crucial element. So we have been able to, publish this work primarily again from Ayuka, and Shomo is the graduate student of Durgesh, who have been able to publish this in again Abjad letter. I will again, highlight a week which was unprecedented last year. I'm sure the PRL team is working also on this week's data, some of the data which they have. I'm giving you examples of what Solex has seen. So from this light curve, you can see there's a huge number of X-ray class flares within a week. Normally, one X-class flare sometimes happens once in a year or once in 2 years. So we were so fortunate to have these huge, X-ray class flares within the first year of its operation. And there is a plenty of very, very, very good quality data. And I know there are people of the X-ray team is working very closely with other collaborators from Solar Orbiter as well. This is the flux with the same period as recorded by the other energy bands, namely the higher energy bands. And as you can see here again, the fluxes are showing these values. So again, comparing the solar low X-ray flux with the high energy X-ray flux, the timing, all these are very important in characterizing the properties of the flares and how these different heating happens, how the material is in changing from the lower atmosphere to the higher atmosphere. Looking through their spectrum, there is certain effect in terms of its ionization potential and all that. Some of that gives you indication about how the material is actually mixing from the lower atmosphere to the upper atmosphere and so on. So there are a lot of science which can be done from there. This is the same period, you have the magnetometer, which is also, you can very clearly see the flux changes, huge flux changes. The timing of these, period also will have to be compared with the source. So this is again the effect or the at Lagrange one you are seeing. Because of that flare, there is a CME which is originating and that is traveling. It takes hours, it can take a day, and then as it arrives, then what is the size of the CME, what is the shape of the CME, what is the kind of magnetic field strength it has. All these can be studied by looking at these magnetic flux changes. And also we have three-dimensional capabilities in terms of BX, BY, BZ measurement. That will also allow you to do some modeling. So I will not get into the details how things are done, but there is a huge potential of working on these fields as well. Now I will get into our coronagraphs spectral data, because at the moment it's only the green line spectral channel which is fully functional. The other channel data, still some experiments are going on, but the data is not really science ready yet. So the coronagraph is one of the 7 payloads on board. It has a unique capability of doing a multi-slit traditional spectrography. This is also again first time we are doing it. So you have capability of getting full spectral information across the slit at the 4 different locations. And the field of view of the spectral channel is only up to 1.5 solar radii. The continuum channel is up to 3 solar radii. And what is shown in the background is a total solar eclipse image for context. Now, ideally, we should overplot with the Proba 3's images, because we will have that. And that is the thing which I want to really highlight, what everybody should look at. So this is an internally occulted coronagraph with simultaneous capability of imaging and spectroscopy and spectropolarimetry. But unfortunately, the imaging channel and the spectropolarimetric channel is still not fully science ready. What we have from the 5303 channel is this kind of signal which you get. I must point out this is quite a tricky business to look at this and process this data. Unless you have a spectroscopic real background, you will definitely make mistakes. What I want to really highlight is here, this is the emission line, and you have these absorption line from solar disk primarily. But this absorption line, it is so close to the emission line because of any plasma motion, there is a danger that this absorption line will get mixed with the emission line. And then you have a possibility of, sort of making mistakes. So this, I think, users should be very, very careful about, how they're doing the line fitting. So I will tell you, this is a pretty sophisticated, high resolution spectrograph with, with very good spatial resolution, the height range and all that. But the data processing is quite tricky. So here I will just again show you one of our student at Aries. She's looking at this data, and we see how difficult it is. If you normally what people have attempted to, just fit a standard fixed profile like this, and then assuming that this is my emission. But as you see that the background itself is actually all the time changing. It is not a constant background. And how you really, this is the shape of the pre-filter, which is not fully calibrated. So we do not have a fully calibrated filter profile. So the filter profile has to be evaluated based on some intelligence. And that we are trying out very different methods. If somebody is doing by a fixed method, the results will not be actually trustworthy. So this is what precisely I'm showing here, that if it is even a baseline fitting with the inverted hat profile, and you see very clearly how the absorption line changes and how the overall profile changes. So you have to be very careful in interpreting this data and do extract parameters. I will again show you some rasters. This is again done by Tonmoy. You do get signal, but you have to be careful about what you are seeing here. So here again, I am showing example how a raster image is created. So these are multi-slit experiment. You have to raster it. You have to move the mirror in a way so that it looks at the different parts of the sun. And here you can create a spectral image, which is very, very nice. And it takes about 12 minutes to 30 minutes, depending on what exposure time you give. And also you can do some kind of spatial binning and temporal binning and so on. In 12 minutes, you can get a raster image, which is reasonably good. But while you do the line fitting and want to really talk about line width or velocity and so on and so forth, you have to be a little careful on this. So that's my really, really clear message. Here again, you see that this is all possible. Beautiful solar active regions, the loops, their dynamics, all that you can study, but be careful about the way you produce this data. Now, next I will move into this new mission called Punch, and I will give the first slide. This is again credit to Craig DeForest, who is the PI, and as you heard, I'm a co-I of this mission. There are several people across US, and some of my earlier PhD students are part of the SOC, and I am closely connected with this. So what is the mission about? It is to understand the sun's corona, giving rise to heliosphere and the solar wind. Again, looking at the closer to the evolution of what things are happening. It has a capability of tracking the CMEs and the stream interactive region all the way from sun to earth. So I will showcase how it is done. There is a combination of a coronagraph called NIFI, near field imager, and WIFIs. These are wide field imager with different field of view. I will come to that. And since they're rotating like that in a near Earth orbit, they are able to produce a 360-degree view of the corona and the heliosphere, all the way from 6 solar radii to very, very close to Earth. I will show some examples. So it has a capability of measuring the solar wind globally in near real time. So it takes about, and I will say there are cadences possible 4 minutes to 18 minutes kind of cadence to generate these images. The extra thing is it is a polarized visible light images. So there are a lot of characteristics or the diagnostics is available because you have polarization measurements available. How is it achieved? It is 4 small sats act as a virtual imager, and this is orbiting in a 650 kilometer sun-synchronous polar orbit. Launched March 11, 25, very healthy. Science operations started. What are the punch signs? It is looking at global evolving solar wind flow, as you will see from an example how it is going to probe the solar wind. It is going to look at the Alvin zone. This is a very, very important zone in the heliosphere, which actually dictates the boundary of the heliosphere. As I said, even from the physics point of view, if you are within the Alvin zone, close to the sun, then one set of equations and one set of physics you can apply. When you are beyond Alvin zone, actually you are more in the kinetic domain. So we do not have so far any observational way to really identify the Alvin zone. It's all been so far theoretical calculation. So first time, observational signatures will be there for the Alvin zone, which will allow the solar wind community and the modelers in a huge, huge way to advance their simulations. And within the solar wind also, you have lots of microstructures. You have turbulence. Solar wind is turbulent. So since you are able to observe these different structures, their evolution, their polarization properties, you'll be able to do that. You'll be, of course, able to track the CMEs, their three-dimensional trajectory, because we have a 360-degree view, as I indicated, that these satellites are revolving in the sun synchronous orbit, always looking at the sun, and it is generating this. I will show how it is done, and then you will, of course, the CMEs produce the shocks in the front as it propagates into the heliosphere, where exactly the shock is, how the shock is propagating, the three-dimensional morphology will be able to be evaluated. So the main idea is, because of the combination of three different WIFIs and one NIFI, we have a comprehensive 360-degree view. So first time you are getting a 3D perspective of the propagation of these structures, and then coding interactive regions. These are the locations where the fast wind and the slow wind are actually interacting with each other, where exactly they are forming. All these signatures will be possible from this. So here it is, earlier observations from stereo. Stereo had to take different instruments to get a comprehensive view. So these are images on board stereo. These are two coronagraph, and these are two heliospheric imager. Whereas Punch will provide you this entire thing in from one mission. So we have from the 6 solar radii all the way to near Earth environment. This is the field of view of the Punch. How it is going to do it? Punch merges images to create a single large field of view. The brightness and polarization brightness images are in pair, and the data products are in 3 arcsecond resolution. So what is it? It's looking at inner limit, as I indicated, 6 solar radii. NIFI outer image is 30 solar radii. So this is very similar to C3 coronagraph, which is there on SOHO. I will show you some example of their comparison. The minimum limit of 4-minute cadence at 80 solar radii to 180 solar radii. So that you can really see that how every 30 minutes, every half an hour, you have a 360-degree view of the heliosphere. So this is the comparison with the LASCO and very recent data from. There's still a lot of work to be done in terms of the cleanup, but applying the principal component analysis from the NIFI, the coronagraph, if you compare with the C3, you will clearly see that there are many more structures which are visible. And one more interesting thing is that these structures are visible up to the edge of the field of view of NIFI. So we'll be able to really study their propagation and their kinematics all the way from 6 solar radii to beyond by combining the WIFI images. So this is just a comparison of the NIFI and the LASCO C3, which is the coronagraph, which is looking at. This is punched in the heliosphere. As you can see, lots of stars are visible. Moon is visible. So they do have a lot of work to really work on how to suppress those stellar lights and other even the Milky Way. There is also a lot of albedo when they pass through close to the Earth reflection. So there's a lot more work to be done, but they're already making the data public. You play around with the data. You could see that you have even you see the neighborhood of Venus here. So 360 propagation of the CMEs after a bit of corrections. I think we are in good shape. Here in this movie, you see the moon, how it goes within the field of view. Punch is fully operational, starts suppressed by 20 magnitude. If corona removed, other effects still remain. You can see it very clearly from the images. Currently running at 8-minute cadence for commissioning. So we are going through commissioning phase, full cadence plan. This was this slide again 1.5 months back. SOC is generating and distributing data products level 0 to level Q. This is a sort of qualified category. Then L1 to L2 photometric mosaics will be coming out, and of course L3 means you have to subtract the background, and that takes a while because to create the background you need sufficient number of observations to create a proper background of the heliosphere. So that's late in the summer. The data is already available. Data is available to the virtual solar observatory. So please visit it and all that. Punch also has the capability of creating this polarization map, and that will give you a RGB kind of map. So here, my former student is a member of the SOC. He has developed a package which will provide you this kind of view of the heliosphere. So this is still things to come. So I think it is high time we move into coordinated observing plan for Aditya L1 and other space platform. This is very, very, very crucial. Aditya mission is a multi-institutional national mission, but I think now it's a high time we go global and work with the global team in terms of the science, coordinated observations and getting the best fruit of it. So that's the status. I will also strongly encourage you, your students to participate in, this particular activity of this Aditya support cell. I'm very thankful to Dibendu and all his colleagues. They're every time very, very supportive and helpful. They're participating very actively in Aditya support cell activities. And I can actually give you some statistics, how many people are now getting interested in looking at, your data as well. So I think these are very important to connect with the younger generation and people at different universities. That's the motto of support cell activity, and I'm thankful to PRL for fully supporting that activity as well. So that's my last slide. Thank you for your attention, and it's a really, really privilege for me to be able to give a lecture on this very prestigious platform. And just to again say that I've just recently come down from the Himalayas. So that's a picture of the Himalayas from our observatory at Devasthal. But I've not included the picture of the Punmuni campus here, which is also equally beautiful. But thank you again for this opportunity.
Thank you very much, Professor Deepankar Banerjee, for this very engaging and informative talk. So we will now begin the question answer session. So I request the audience to please type your questions in the chat or use the raise hand feature if you would like to speak.
Should I stop sharing or because I can't see otherwise anything? So
yeah, sure. Yeah, I think you can stop sharing, and if required, you can share again.
We can come back to that. Yeah. Okay.
Yes.
Yeah, Pallam
so, I can see Professor Pallam Raju. So Professor Pallam Raju, please, ask your question.
Yes. Thank you. Thank you, Deepankar, for this excellent talk, giving us a very, in a capsule, what is all happening in the recent past, and what are the potential research areas in the near future. Wonderful lecture. Enjoyed it thoroughly. The question I wanted to ask, is a couple of decades ago, in the UCAR group had predicted, based on physics-based models, high solar activity, but what turned out to be a low solar activity. So, in that regard, what has been the missing element, and has there been any updates on that, so that in the next predictions in the physics-based models, we can do a better job?
Yeah. Since you asked this question, this is another domain, but you are right. in fact, the predictions were so varied. Some people predicted a weak cycle, some intermediate cycle, and some very, very strong cycle. Even when you say physics-based model, they are actually dependent on certain parameters, which do not have a direct way of measuring it. For example, the diffusion, how efficient is the diffusion of the magnetic field inside the convection zone. So it appears that the models which predicted a higher strength considered a high magnetic diffusivity and so on. So whereas if you take a lower value, you get a different time scale, and that did predict actually slightly weaker cycle. So we have not reached that maturity to make a really precise measure sort of prediction. Having said that, there are improvement on that, but in reality, what is happening is that the process is very much stochastic, and it doesn't have a strong memory. So in principle, actually, you cannot predict the solar cycle, even physics-wise, very much well in advance. You can probably do it a bit more, I would say, efficiently half a cycle before. Essentially, when you have a minima, then probably you can say what would be the maxima and how strong it will be and so on. So we are still with 20-30% error, but it was reasonably known that the current cycle will not be as strong as one much before. So the last cycle was also weak, and this cycle also seems to be slightly stronger than the previous one, almost comparable to the previous one.
Okay, thank you. I have one more question. Bhuvan, is it okay?
Yeah, sure, please.
So that is regarding the Proba 3, data that you showed, because these are the satellites which are continuously on orbit. So what is the kind of change in the spatial extent of the features of on the sun that are coming out, and is it within the limits of the existing models, or new codes have to be written for understanding that?
No, first thing is that these two satellites, they can only see the corona in the formation flight, with this configuration of eclipse, which has to maintain this precise 150-meter separation and all that. So they're not going to attempt to get into this configuration all the time, because it is very hard, particularly when these two satellites are closer to the Earth. The pull is so high, to maintain that separation will be formation flying will be very, very difficult. So they are only going to do 6 hours in each orbit kind of thing. So that's the current. So it is not a continuous observation of the corona at all. So this is one limitation. But that's why it is more important to know when they are going to be in the eclipse configuration, so that we can run our observing mode, which is complementary to this. So they will not have this. So in a way, the separation or the coronagraphy thing which they will achieve is more or less around the same location in this low Earth orbit. Since we are always in the low Earth orbit, you see, your question is more relevant if it would have been a solar orbiter kind of situation, where we are really traveling much more into the heliosphere, and the scale changes continuously. So here, whenever we are doing the formation flight at the farthest distance away from the Earth, it's reasonably within few hundred to 1,000 kilometers, I would say. So that's not going to change this overall size and so on of this. So we will be always looking at 1.1 to 3 solar radii. But you are right, if it would have been solar orbiter kind of path, or even the Parker, there continuously the field of view itself is changing.
Yes, thank you. Thank you.
Yeah, thank you very much. I think somebody has changed my layout, and I am not allowed to change it again. But I before that I saw 2 questions in the chat. Yeah, now my layout has come back. So I saw 2 questions in the chat that I would like to read out. Where is that chat box has gone somewhere because of the change in the layout. So in the meantime, may I request
could see the chat box. Should I read it?
May I request Durga to read out the question?
Okay. Okay, Richa and Jayan is asking, sir, it was a wonderful talk. Can you please share the little more about corona polarization brightness and how does Punch produces these polarization maps of the corona and inner heliosphere? Yeah, this is a little, yeah, thank you for the question. It is a little involved because as you know, the polarization images has to be taken in the 3 different orientation. So you have many different ways of doing the polarization measurements. So they are going to do in 3 different angles. So which is separated by this kind of 360-degree view. So they will take the images in 3 different angles by rotating the polarizer, and that will reproduce the image eventually. And that I was just very briefly telling about. You can try to reproduce that in terms of a RGB color map. So that is what Ritesh was trying to generate, and they will produce these kind of polarization map in RGB, basically representing 3 different polarization angle perspective. Okay, so the next question is Rutvik Madhak. Hello, sir. In few books, basic temperature of the core is 1.5 core Kelvin. How can one calculate that? Okay, so I did not talk about it at all. So in the core of the sun, the nuclear reactions are taking place. We know hydrogen gets converted into helium, and there are neutrinos which are generated and all that. So at what temperature these hydrogen gets converted into helium and this PP chain reaction takes place, there is a subsequent knowledge about it. And how much neutrinos in that process are also likely to be generated, also known. So we do observe the neutrinos. So that is again sort of coming from the interior or the core temperature. So that's one way of knowing it. If the temperature, of course, to start the hydrogen burning, you need certain temperature. So that's also gives you a theoretical clear cut requirement of this 1.4 million Kelvin temperature. So you have said 1 crore, okay, million, I get still confused. 1.5 15 million Kelvin temperature you need there. Yeah, so that's the way we. Of course, there are stellar evolution models and all that. That will also give you a strict constraints about what would be the temperature inside the sun.
Yeah, thank you. So I can see that Dr. Divyendu Chakravarti has raised his hand. So Divyendu, please ask your question.
Yeah, it was a great talk, and it is just give an overview. Enjoyed it thoroughly. I just have a curiosity question that you see Parker Solar Probe, they could detect the Alvin layer because when it crossed the Alvin layer, that is the time they actually can say that they have touched the corona. Now, in case of Punch, how do they plan to do it? Because you say that one of the goals of Punch is to talk about the spatio-temporal evolution of the Alvin layer. I'm just curious to know how do they plan to do it.
Yeah, it's a very good point. And as you rightly pointed out, because Parker is crossing the Alvin surface, so they have a signature or a bump or a dip of certain parameters which will dictate, but this is not a continuous, of course, way of doing it. So this is remote sensing. So what is proposed is, you will have some density structuring, and also you will have some nature in terms of the turbulence. So since it has a capability of some way of estimating the turbulent nature of the heliosphere at different radial distances away, from that it is expected that we will be able to really almost like see that layer or surface, because it is not a layer, because it's a 3D object, it's more like a surface, which will give you an indication that that's the radial distance away which is giving that. This will be also linked with the solar wind map. So they will have a possibility. One of the data products which they propose to provide is the solar wind map, like what you have from Ulysses, for example, once in one per orbit. Here, I think every month you will get a solar wind map as well. So those are the 3rd level data products which they will produce.
Okay. Thank you. Yeah.
So I can see that this raise hand icon in the computer in our seminar hall. So before that, I would like to request our director to please ask his question, and then we will come back to the seminar hall.
Thank you, Bhuvan, and very nice talk, Dipankar.
Thank you. Thank you.
Very enjoyable and very informative, because
Thank you.
we get quickly a lot of information in such talk. So my question is more on little bit of technologically understanding, because the orbit of the Proba 3 is highly elliptical, right?
That's
It is something
correct.
like by 600 by 60,000 kilometer kind of orbit,
Yeah,
highly
yeah,
elliptical orbit,
yeah,
right?
yeah.
And so in this highly elliptical orbit means orbital period would be somewhere close to 20 hours or so, right?
Yep.
So how long do you see a continuous solar eclipse during this one orbit at
Yeah.
least?
So they mentioned it. It's a very good point. Maximum 6 hours.
Maximum 6 hours in one orbit.
Yes. And that also, because every time where they go into that, they will need fuel. So they're really calculating that whether they will do it in each orbit or, subsequent few orbits and then again stop for this. Is actually a discussion was going on a couple of weeks back. Initially, they thought that they will give 6 hours once in few orbit. That was the plan. But now what happens is sun is active. So if there is, a lot of activity happening and all that, they were giving this opportunity to the science working group to decide on whether consecutive orbits, they will be giving you this eclipse conditions, but then several weeks you will not get the eclipse conditions again. So which one you prefer? So this is a discussion going on. But each orbit, you are absolutely right. They can only achieve maximum 6 hours of these eclipse conditions.
Okay. So 6 hours, and whereas for us, we can get a continuous coverage using VLC, right?
Yeah.
So that's the big advantage for us.
Of course,
we get
L1,
continuous.
it's L1.
Yes.
Lagrange 1 is a fantastic vantage point for solar remote sensing.
Bhuvan, can I ask you one more question?
Yeah, sure, sir. Please.
So when you look at the eclipse, which is artificially created by our Proba 3, vis-a-vis the Aditya L1, the overlapping region is how much?
It's a perfect overlap because, VLC, unfortunately, the spectral, field of view is 1.05 to 1.5. The continuum channel field of view is 1.05 to 3 solar radii. And Proba 3, the field of view is 1.1 to 3 solar radii. So it is perfect overlap with continuum channel. But since we are not able to still produce a continuum channel, images, we are not able to compare. But at least this 1.05 to 5 solar radii, we have a spectral information. This is the beauty which Proba 3 do not have. Proba 3 has green line images, spectral images, but we have spectra. So you can do sit and stare, you can do spectral imaging by rastering, and that you should compare with Proba 3 in conjunction will allow you to do more diagnostics.
Good, great, thank you.
Thank you. I cannot find any further question in the chat, and also I cannot see any raised hand.
The seminar room still has a raised hand.
Yeah, I can see this raised hand icon in the seminar room. So please ask your question. Perhaps it is done by mistake. So yeah, or you can type your questions as well in the chat.
What are the scientific benefits that justify the additional technical challenges introduced by using a separate spacecraft only for the occulter?
Sandeep, can
if I could hear him properly,
yeah,
he's asking
cannot
what is
hear
the
you
scientific...
properly. Can you come close to the computer? Yeah.
Can you hear me?
Yeah, we can.
Okay. First of all, thanks for this wonderful talk. And my question is regarding Proba 3 mission. So regarding Proba 3, what are the scientific benefits that justify the additional technical challenges introduced by using a separate spacecraft solely for the occulter?
Okay. Yeah, it's a good point. Of course, this formation flying with such precision, autonomously doing in space has a lot of future technological requirement. These are called technology demonstration mission under ESA's program. And what we try to do is utilizing that technology demonstration for our science. So the basic thing is driving this formation flying with such precision of few millimeter. This docking, you heard about the docking. So this docking is very important for space platform transfer. Suppose, you want to transfer fuel to another spacecraft in future. You want to power the other spacecraft. So this docking is very, very important. So controlling two satellites, two objects in space, which is moving with a different speed, maintaining their separation itself is a big exercise. That's why, the SpaceX, we are just doing that docking experiment, not too much science on that at all. Here we are getting additional thing. I did not mention the first satellite, which is acting as an occulter, also has a radiometer. So which is measuring the solar flux. So there is a solar radiometric experiment on the first satellite, which I did not talk about today because I was trying to focus on the eclipse. And as now you see from the result, from space, we are able to first time able to generate a inner corona view of the sun with so close to the sun up to 1.1 solar radii. I must admit, Aditya's one of the main objective was that to reach as close to the sun to see the coronal features, and they have achieved this, and they are able to reproduce it as and when they want. So I think that's a fantastic achievement. So it will have additional science output from a technology demonstration mission. So that's the way it worked. The technologist and the and the scientists together.
Okay, thank you. So Professor Nandita, please, ask your question.
Yeah, thank you, Deepankar, for a very nice and informative lecture. It has a field of view starting from 6 solar radii to 180 solar radii. Is it so firm, this boundary? And if so, it would have been interesting to follow a CME from the sun, from close to the sun to the earth. But this is sort of limiting its, kinematic study up to the earth, because you are missing like 30 to 40 solar radii before it reaches the earth. So how one can compensate for that?
Yeah, that apparently is a even more challenge. I mean, 180 itself is becoming very big challenge because of the Earth's emission. That is spoiling the albedo and all that, because these are, sun synchronous orbit. They're already struggling with this. So going beyond what they have, I think will be almost impossible to target. So because you have to realize these are same heliospheric imager looking at a large wide field of view. So if any planet comes in between, the radiation from the Earth itself and the radiation belts and all that, they're all affecting the image very, very dramatically. So I don't think from the same instrument it is not possible. That is what stereo has done. You see, stereo has done, 2 coronagraphs, 2 heliospheric imager. So by having,
but even there, you had a problem in HI2.
That's right,
We were
exactly.
not able to see the diffuse emission from the CME that was going.
Precisely. So it is much beyond now. They have able to they have, hopefully, because a lot of corrections are still necessary. You saw the near the Venus, how much brightness was there. Because you are talking about going beyond Venus, so that will be quite a bit of a challenge. Yeah.
Yeah,
You have
and
to have a
another
separate
thing,
instrument, separate
yes.
imager looking at that, field of view alone.
So another thing you didn't mention, maybe you mentioned and I missed it, about the lifetime of this mission, both these missions.
Okay, good point.
What is
Good
the
point. Good
duration?
point. So PROVA is a strictly 2 year. PROVA is a strictly 2 year from the commissioning. But again, this is technology demonstration, will depend on how much ESA's, resources they want to use it. Because sometimes what happens, once you technologically, you demonstrate your capability in terms of monetary things, it is hard for ESA to support it. So I think it is for the scientific community like us as to, prove that it is really worth extending it. Having said that, there is also a huge constraint on the amount of fuel which is will be available, because every time they do a formation, there is a good amount of fuel which is required. That's what I understand. Whereas punch is also a nominal 2 year, but we expect 5 year life for punch. And what happens typically, one can argue that solar wind will be changing and all that. So this is a science mission. This is not a technology mission. So hopefully they will have extension.
Extension.
Like Soho had a 5 year nominal mission, still it is
Still running, yeah.
observing in more than 2 solar cycle. So I think it is a scientific merits will have that extension.
Okay, thank you.
Operationally, I understand 5 years should be natural. Yeah.
Thank you, Deepank.
So thank you. So I cannot see any further question, but still, I can see this hand is raised, in the seminar hall. So if there are any further questions by students, so I encourage them to ask their question. So no further questions. And also in YouTube, I cannot see any further questions. So thank you very much, Deepankar, for this wonderful talk. And now I would like to request my colleague, Dr. Bala Murugan, to propose a vote of thanks. Over to you, Bala.
Thank you, Dr. Bhuvan. It is my pleasure and honor to propose the vote of thanks. We have come to the end of an interesting talk and the end of 106th PRL ka Amrut Vyakhyaan. Thank you, Professor Deepankar Banerjee, for sparing time for us and delivering a wonderful talk. You have taken us close to the sun and have provided us, you have provided the audiences an update of the science of our own sun via solar system remote sensing. This Vyakhyaan is one another great value addition to our Vyakhyaan series. This talk will be available for anyone to see at any time in the PRL YouTube page. Many thanks to our audiences and thank you for those interesting questions. Thank you to Director, Dean PRL, Professor Nandita, Amrut Vyakhyaan committee members and all the PRL members. This is the chain that keeps the PRL Vyakhyaan pulsing forward. Before we conclude, on behalf of the members of PRL, I would like to thank our speaker once again. Thank you, Professor Deepankar Banerjee. Stay tuned for the next
Thank you.
one.
I've enjoyed the interaction also very much. Thank you for this opportunity.
Thank you all.